Okay, so we are now live. I will make this introduction, a short introduction. I will let Rosângela say a little bit more about you, Eduardo. So I'll switch to Português. Pessoal que está assistindo, boa tarde, os alunos aí, vamos entrando todo mundo aí. Então, está começando agora o seminário do Eduardo Gutiérrez-Peña, da Universidade Nacional Autônoma do México. É um prazer ter ele aqui com a gente. O Eduardo, bom, além de trabalhar, pesquisador na área de Bayesiana, enfim, ele fez licenciatura em atuária, né, pelo que eu vi pelo currículo dele. Ele foi mestre em estatística pela UNAM e doutorado em estatística no Imperial College. Eu convidei aqui a nossa coordenadora do programa de pós-graduação, Rosângela, que é amiga do Eduardo, para fazer um pouco a introdução dele também. Então, seria legal ter ela falando um pouquinho. Rosângela.
Muito obrigada, Vinícius, pela oportunidade. Eduardo, I will just speak in Portuguese. Fine. Just to say some gossips about you. Okay? It's a great honor to receive you here. Unfortunately, it's not live, but it will be one day. It will be possible one day you visit us here in Minas Gerais for you to know our department and take some cachaças with us. And it's a good place, no, to visit. I hope it will be very soon. Meus queridos alunos, né, boas-vindas aí ao nosso semestre. É o primeiro seminário do semestre, então eu acho que nós estamos com muita sorte, porque o Eduardo é um excelente apresentador. E eu tenho que fazer fofocas do Eduardo, porque eu já conheço o Eduardo já há algum tempo. Além das coisas que estão no currículo dele, né, que o Vinícius falou, o Eduardo é uma pessoa extremamente ativa, não só na vida de pesquisador, de orientador, né, mas também na vida de divulgação da ciência, né, de promoção da ciência na América Latina. Então, ele é um dos líderes, né, da América Latina na área de estatística bayesiana. Ele faz parte do grupo que criou o COBAL, que é o Congresso Latino-Americano de Estatística Bayesiana, que foi feito para a gente divulgar a estatística bayesiana na América Latina como um todo, e também a gente descobrir, né, o que as pessoas dos países vizinhos estão fazendo na área. Não só ele fica junto com esse grupo de pessoas encontrando gente para organizar eventos, né, mas ele mesmo organizou vários, porque o México já sediou 2 COBAL, e nos outros que foram organizados, ele sempre esteve no comitê científico e organizador, ajudando as pessoas que lideraram a organização nos seus respectivos países. O Eduardo também, ele serviu várias vezes, ele foi presidente da Associação Mexicana de Estatística e ele esteve no quadro de diretores dessa associação por alguns mandatos, na ISBA, na International Society for Bayesian Analysis, editor associado do Bayesian Analysis Journal e do Chilean Journal of Statistics. E esse eu vou frisar, foi do Statistics também, mas o do Chilean Journal eu vou dar um destaque especial, porque o Chilean Journal foi um projeto reativado por uma grande amiga nossa, que foi a Pilar, e ela, infelizmente, ela faleceu antes do periódico voltar à ativa, né? Então, o Eduardo está num desses grupos de amigos da Pilar que ajudaram a reestabelecer, né, o Chilean Journal of Statistics, que antes era a revista da SOT. Então, Eduardo, it's really a pleasure to receive you here. I hope you can see very soon. I see you after the seminar in our seminar soon. Now you can. The word is with you now. Thank you so much.
Okay. Thank you, Rosângela, for a very nice presentation. Thank you, Vinicius, for the invitation. Okay, so this is a photo of the first COBAL Rosângela was mentioning. She's been very modest because together with Pilar is around here. Can you see the mouse cursor?
Yes, we can.
Okay, thank you. Pilar is right here on the right. Together with Pilar, Rosangela has been promoting these events for a long time. This is the first one in Ubatuba, almost 20 years ago. Here's Rosangela, smiling as always. I am hiding somewhere here. And this is a very, very special event for me, and I'm sure for her también, because it's a very nice effort from the Latin American community to push the Bayesian school, and I think it's been very successful. So I hope we can carry on with that effort. This is a picture from the second Cobal. I cannot see myself here. I swear I was there, but I don't remember what I was doing. Or maybe I managed to hide behind someone. No, here I tried but didn't manage. Here I guess I managed. This is from the third Cobal in Chile. This was organized, as Rosangela mentioned, by Francisco, by Pancho. He is here. Unfortunately, he is not with us anymore. He passed away a few years after this event. It was a very, very nice event in Chile. This is a working session. We were working very hard, also in Chile. As you can see, I'm perhaps, I don't remember well, but perhaps thinking about the following Cobal. And this is the last picture I got. This is from Medellin, almost 10 years ago in the fourth Cobal. And I'm sure you can recognize a lot of people here. This is Dani, Rosangela smiling again, and a lot of colleagues from all over Latin America. So it's very nice being here. I am very pleased, and I thank you again for the invitation. Well, what I'm going to talk about today has to do with some work I've been doing with Luis Enrique Nieto from ITAM, a former student of mine at the master's level. He went on to do his PhD under Stephen Walker, and he's been working on this kind of models for a long time. But what we did in this work was try to put together several pieces of work and try to organize them under the umbrella of the exponential families. Luis Enrique has been working on these for particular cases, for example, beta processes or gamma processes, and both distributions belong to the exponential family. And when you see something working for several of these models, it's very easy to think that it will work for more general exponential families or for classes of exponential families. So this is the case for this structure that he's been working on. And this kind of models allows to produce or introduce dependency structure on a set of random variables in such a way that we can have strict stationarity. And this is a very nice thing because traditional models only achieve this in particular cases, and in most cases, it's not that easy to achieve. So this is the layout of the presentation. I'm going to start by briefly reviewing the classical models for time series, a la Box and Jenkins. In those cases, the emphasis is in normal models, normals with errors with normal models, sorry. And most of the models rely on this kind of structure, like autoregressive structure, where we have this linear kind of dependency, or moving average structures like the one below, where we average lagged errors. And under some conditions, we can get stationarity. For example, for the autoregressive processes, we can only get second order stationarity. Under certain conditions, when we consider the infinite sequence, the infinite process, if n is finite, then there are no conditions known for strict stationarity. Only for the normal case that happens, but in general it's not possible. For the moving average process, again, we can only get second order stationarity, but not strict stationarity, even for the infinite series. And if we only consider a finite collection of variables, there are no known conditions for strict stationarity, which is a desirable property to have, strict stationarity, guaranteeing that all the variables in the process have the same distribution. Concerning spatial models, there's, also models relying on linearity and normality mostly. This is the case for the conditional autoregressive process, which is very similar to the autoregressive process we saw before for a temporal series. And again, it's difficult to get nice conditions for strict stationarity. In this case, we need to impose several restrictions on the coefficients in order to have stationarity. So it's interesting, it's useful to think about ways of generating models for time series or for spatial processes in such a way that we can achieve this stationarity. This is previous work by Luis Enrique together with Alejandro Jara from Chile and Fernando Quintana also from Chile. They devised this hierarchical model in such a way that they could introduce these dependencies between variables. For example, in the diagram we have here, we have a process of degree 3, or order 3, where these observations are related to latent variables S1 up to S5. And say, for example, S1 is influencing the distribution of Y1, Y2, and Y3. S2 is influencing the distribution of Y2, Y3, and Y4, and so on and so forth. So this is a graphical representation, but we can think of this as a hierarchical model where the observations at the level below have a beta distribution conditional on a series of random variables S. These latent variables have a binomial distribution, a discrete distribution in this case, which depends on a parameter U, and U itself has another beta distribution. This construction guarantees that the marginal distribution of the Y's is also a beta distribution with hyperparameters A and B, and depending on the choices of these parameters N, we can obtain strict stationarity, but we can also model other kinds of behaviors. So the idea is trying to generalize this construction to more general exponential families. This is just the example of a beta process, but we would like to generalize this to other exponential families. So with this background and my own background on exponential families, that's some work I did many years ago for my PhD thesis, it was sort of natural that we would go together on this kind of topic. We are also interested in spatial and spatial temporal dependencies. This is a simple example. For example, where we have this diagram, and Y3 is related to all other 4 variables, but say, for example, Y1 is only related or neighboring Y2 and Y3. And this is the kind of structure you could get. For example, S3 is influencing all the Y's, whereas S1 is only influencing Y1, Y2, and Y3, for example. But anyway, any kind of spatial structure can be accommodated in a similar way. So let me proceed with a brief review of exponential families, mostly to set up the notation. We consider a random sample of n observations, ID observation from an exponential family with a probability density function of this form. And this is the canonical form. An exponential family, as you know, can be written in several ways, but this is the canonical form. Theta is a canonical parameter. S is a canonical statistics, which turns out to be sufficient statistics for this family. M is a so-called cumulant transform, and in some ways characterizes this family. And I'm sure all of you know that this exponential family has very nice properties, is very tractable, and also contains several of the models that we used in most applications. You know, most simple distributions that we use belong or are related somehow to the exponential family. So it's a very nice family to work with. It's also closed under convolution in the sense that if we consider the sum of these statistics for the sample, that distribution is also an exponential family, and I will be using this form. It has density of this form. Bs, in a way, is a convolution of this function A x, a of x, and it has very nice properties. For example, in terms of convexity, that makes the analysis very simple, and also posterior simulation from models relating to this family are also very easy to set up. Let me go back to this. Let me consider for the moment the statistic, the canonical statistic corresponding to a single observation. Yeah, this is mostly for convenience, but because of the linearity of the statistics, we can see this for a more general n. But in this case, it's simple to use only one observation. So in this case, the cumulants of S, particularly the first moment and the second moment, the mean and the variance, can be obtained simply by differentiating the cumulant transform M. So the expected value of S is just the gradient vector with respect to theta, and the variance of S, the variance covariance matrix of S, is just the Hessian matrix with respect to theta. So it's very nice, it's very easy to obtain these first two moments. And there are also formulas for higher order moments, but for the moment this is what we need, and that's enough. It's convenient to work in terms of the canonical parameterization for most things, but in terms of applications, it's usually better to work in terms of the mean value parameterization. It's nothing more than the expected value of S, and as we saw, this is just the gradient vector of the first derivative of the cumulant transform. Let me call mu that transformation. Mu is also the mean value parameterization, and I will call omega the parameter space for this mu, just the image of theta under this transformation. Theta, capital theta, is just the parameter space corresponding to theta, the canonical parameter. Another concept that will be useful in this presentation is the variance function, which is nothing more than the variance of S, but written in terms of this mean value parameterization. And this is just H evaluated at theta of mu. And this is defined for mu on omega. Morris, many years ago, proved that this pair, the variance function together with the support of mu, characterizes the natural exponential family. So that's very nice, and also it's interesting that only a few families satisfy a certain condition that we're going to use, which is that the variance as a function of mu is quadratic. That's going to be an important property for this talk. Well, for the purposes of this talk, I will be mostly working in terms of the mean value parameterization, because that's more natural in a way. It's in the same scale of as the observations, so it has a nicer interpretation, which doesn't depend on the form of the family. It's just expected value of S, whereas the canonical parameterization doesn't have that nice interpretation, not all the time anyway. So one thing about exponential families, and I mentioned that it was very tractable, and that can be seen, for example, in the classical Bayesian analysis of the model. If we consider conjugate priors for these sampling models in the exponential family, particularly in the natural exponential family, we can see that the prior distribution of the prior family is also a conjugate family, and will inherit many of the nice properties of the sampling distribution in a way. So here I'm writing the prior in terms of the mean value parameterization mu, and this is the conjugate prior induced by the conjugate prior of theta. It's not directly the standard conjugate prior of mu, and you can see that because I'm considering here the Jacobian of the transformation, and this is because in general this prior will always exist, whereas if I consider the standard conjugate prior in terms of mu, that sometimes is empty, so it doesn't really help. But in this case, this guarantees under very general conditions that the prior family will exist, it's not empty, and then we can work with that. So this is the Jacobian, and it's related to the variance function, just the inverse of the variance function when written in terms of mu. So if we start in a typical analysis of data with a sampling distribution belonging to a natural exponential family, and we take a prior in the conjugate family, precisely because of this property of conjugacy, the posterior distribution will also belong to the conjugate family. And we can update, we can go from the prior to the posterior in a very simple way. In fact, in this case, the rules taking us from the prior to the posterior are just additive. Yeah, the canonical statistic, so to speak, for the posterior is just the sum of the canonical statistic for the prior and this observed canonical statistic, and the precision parameter is just the sum of the prior precision parameter and the sample size. So we will mimic this structure in order to construct these processes, and in order to achieve, if that's the case, if we want to achieve strict stationarity. So within the class of natural exponential families, I said we are going to concentrate on the class of variance functions that are quadratic. In the case in the univariate case, sorry, that means that literally the variance function is just a quadratic function of the mean. So K0, K1, and K2 are just constant, are just coefficients. And Morris proved that there are only 6 families that satisfy this condition. As you can see, this list contains some of the families that are most used in applications. You know, the normal, the Poisson, gamma, binomial, negative binomial. Perhaps the only exception is the hyperbolic secant, which is a distribution not unlike the normal, is defined over the whole real line, but it's not very well known and is not that used in application. It's an interesting case anyway. So these are the basic elements of these families. Of course, any affine of linear transformation of random variables having any of the distributions will also have a variance function which is quadratic in the mean, and the coefficients will be different. In this case, all these k's are 1 or minus 1, but these are the basic elements. So it's a very rich family. I mean, it's small in a way, only 6 families or subfamilies, but it's very rich in the sense that the distribution it contains are very useful, are very well known, and so it's an important family. That's one of the reasons we decided to concentrate on this family for this work. The other one is that for this family, it is possible not only to find explicitly the expected value or the posterior expected value of mu, but also its variance. And that will help us when we look to find the form of the correlations or autocorrelations between the observations in these kind of processes. So that's the main reason. Okay, so as I said before, we're going to mimic this structure, and we're going to take the prior or the form of the prior as the distribution we want for observations. And as I said, we can make that distribution, or we can make that process to be strictly stationary. So that means that it will have the same form as the posterior, and we are going to do this through a hierarchical model. So the general framework is the following. Again, we will only be dealing with the univariate case, and we will start with the distribution of mu, which is kind of latent variable. And the distribution of u defines also the distribution, the marginal distribution we want for xy. Xy will be the observed process. So this will be, as you can see, a distribution on a conjugate family, but this is a conjugate family which is conjugate to a natural exponential family with quadratic variance function. That's the basic assumption we're making here. So this will be the form of an exponential family, or the sampling distribution of an exponential family having a quadratic variance function. But in this case, this is not representing observations. It's just a latent variable. The observations will be given by the y's. This is the observed process. So at the first level, we have this latent variable u with this distribution. I mentioned already it's conjugate to a natural exponential family with quadratic variance function. But I also mentioned this is also an exponential family itself. So that makes things nicer and easier. Conditional on mu, we will have a set of latent variables S, which will have a natural exponential family, And these latent variables can be either discrete or continuous. In the example I showed before, where this was a beta distribution, this was a binomial distribution, so we can have also discrete variables here. And finally, conditionally on the latent variables S, we have that the distribution of the observations of the observed process is also from this exponential family, which is conjugate to F. Yeah, it is and has the same form of the distribution we use for U. So as we're going to see, the main result, or one of the main results of this work, is that the marginal distribution of the Y's is exactly the same as the distribution of U. So if we choose these parameters N, J in a convenient way, we will in particular achieve stationarity, or we can model several other kinds of dependencies. So in what follows, we're going to talk about neighbors, regardless of whether we're talking about time series or spatial processes. For temporal dependence, for example, of order Q, the set of neighbors will be just the last Q elements from I minus Q up to I. For spatial dependencies, this will be literally the neighbors, defined in a convenient way. And for spatial temporal dependence, we can work with union or cross product of these sets, right? Sorry, I'm not looking at the chat. If you have comments, it's probably a better idea to wait till the end, because I'm looking at the presentation. Right. So this is our main result. Suppose we have a process characterized by these three distributions in this hierarchical setting. And then, as I already mentioned, the marginal distribution of each UI is the same as the distribution of U. And we can choose U from a set of certain exponential families, depending on which of the 6 families I mentioned we decide to work with. And the second result is that we have an explicit expression, and a very simple one, for the autocorrelation of this series. Yeah. So for any 2 random variables, x, y, and xk, the correlation induced by this model has this very simple form. And as you can see, basically they are only depending on the precision parameters of the exponential families, yeah, of the family at the second stage, and also the precision of the prior and not. So it's a very nice expression, and it's very general for all these exponential families. And it's very useful because it's also easily interpretable. And then we can, as I said, set or model different kinds of dependencies, choosing in a convenient way this N naught and NJ. So here are a few examples. We have on the left panel the autocorrelation functions for a situation where we fix N naught, the precision of the prior at the top level of the hierarchical model. We fix that to 0.01. This is a solid line. And we also have, for example, and this is fixing the NJs for the model at the second level of the hierarchy, all equal to 1. Then we increase the value of N naught. This is 1 for this case, and maintain all the other n's equal to 1. So we get this red line, the dotted line. But we can also get less stable autocorrelations in a way. Say, for example, here we are using different values of n at the second level of the model. And we can have ups and downs, as you can see in the autocorrelation. So it's very flexible. It can model several different types of dependencies. On the left, on the right panel, we have several simulations. Instead of fixing the values of n on nj, we just simulated them. In this case, n naught from a uniform distribution on the set on the interval 0, 2, and the nj's were simulated from a gamma distribution, as you can see, with parameters 1, 1 in both cases. So this is just for illustration, just that you can see the different types of behaviors that the correlation function can have under these models. That's for temporal dependence. In the case of spatial dependence, well, we chose to show the different possibilities in this kind of diagrams. Here, just plotting the correlation between the different regions. For example, this first line is 1 because it's the correlation of the region 1 with itself. And then we have the correlation of region 1 with the other regions in the diagram I show at the beginning of the presentation, and the same for all other regions. And we did the same kind of exercise. We fixed, for example, the precision parameters at the second level all equal to 1, and played around with n0, the precision parameter for the model at the top level. And then we also moved the values of n for the model at the second level while fixing the first model equal to 1. So you can see we can also model several kinds of dependencies, even in the spatial case. So what I'm going to do now is to discuss each of the six possibilities. Remember, we have 6 natural exponential families with quadratic variance function. So each of those will provide one process, and we are going to look at them one by one. So, for example, we have, in the case of the normal distribution, where the variance function is constant, we have normal distribution for u, and this will also be the marginal distribution, even the stationary distribution, if you want, of the observed process y. And because of conjugacy, what we have is the latent variables will also have a normal distribution, and conditional on s, this will have also a normal distribution. But marginally, remember, we'll have the same distribution as u. And this is just to show the form of these different canonical functions for this case. Mu, in this case, is the identity function. The cumulative transform written in terms of u is just a quadratic function, and the Jacobian is just constant. Remember, this is the inverse of the variance function. As I already mentioned, this is a constant. It's convenient to write or rewrite this in terms of a more familiar parameterization. So if we call mu S0 over S0 and tau equal to the precision, the prior precision n0, then we can write the model in this way, which is probably more familiar. Yeah. And well, in the proposition I showed you a few slides ago, we have a general expressions for the correlation, and it will be written in terms of tau and the ni's in this case. So this is a well-known model, but this can be seen as a particular case of the structure we are developing here. The second example is a gamma process. We have a process with gamma marginals. And what we have is that the sampling distribution at second level is a Poisson distribution. Yeah. So this is similar to the example I mentioned before, where the second level had a binomial distribution, a discrete one. In this case, it's a Poisson distribution. Conditionally on these latent variables S, the observations Y will have a gamma distribution, and then marginally we'll have the same distribution as gamma. So the canonical functions in this case are log u, the identity function for m, and 1 over mu for the Jacobian. Again, that means that the variance function is just mu, as should be, and that's a polynomial of order 1. So it's within the quadratic variance function family. And again, we can just change the notation to make it a bit more familiar for us. And if we have a gamma alpha beta distribution, we will achieve the same distribution, the same marginal distribution for the yi's. And as before, the correlations will be written in terms of eta and the ni's. So for the inverse gamma, we need the gamma distribution at the second level. Instead of a Poisson distribution, we have the gamma distribution at the second level. And then we will have an inverse gamma marginal distribution both for E and for the yi's for the observations. And these are the canonical functions. In this case, we have a proper quadratic variance function, which is the inverse of this Jacobian function here. And as before, we changed slightly the notation so we can find it a bit more familiar. And this is the structure of the hierarchical model in this case. This is the same model I used as an illustration, the one Jara, Fernando, and Luis Enrique worked a few years ago. Here we have, for the second level, a binomial distribution, and for the first and the third level, we have beta distributions. So we have beta marginals. And as you can see, all these canonical functions have, in these cases at least, very nice forms. They are very nice functions, the logistic in this case. And the inverse of this you can recognize as the variance function of Bernoulli distribution, u times 1 minus u. If we change the notation again and talk of in terms of alphas and betas, we get basically the same model as Luis Enrique worked before. For the negative binomial, if we think of negative binomial distributions at the second level for these latent variables, what we get is an inverse beta distributions for u and for the y's. Yeah, and this, well, there are other names for these distributions, but this is basically distribution defined over the positive real line. And a simple transformation will take us back to the interval 0, 1 and to something similar to beta distribution. But this is what we call it, the inverse beta distribution, in analogy with the inverse gamma we saw before. So if we do that, we will have the same structure. We can also change the notation to make it a bit more easier to read. And we will have a marginal distribution for the u's, which is inverse beta, and also the marginal distribution of the y's will be the same. And as before, because we have the general result, we have that the correlations will involve alpha and the ni's. And finally, we have this distribution we call the scale student t, which is related to the hyperbolic second distribution I mentioned. It's the sixth member of the family with quadratic variance function. It's not very well known, but I guess it could be useful in some cases. The corresponding distributions have heavier tails than the normal, so it could be useful in those situations where heavier tails are required. In this case, if we assume that the latent variables at the second level have this hyperbolic second distribution, then the corresponding marginal distribution for u will be this scale student t distribution with this density of densities of this form, and that will also be the distribution, the marginal distribution of the observed process y. So despite the form of distribution, it's not as nice as the previous one, but despite the form, is still a nice family to work with because it has a quadratic variance function. Look at the canonical functions, they also have simple forms, and this shows that the quadratic variance function is also quadratic, the inverse of this. And we can write it in a more familiar way in terms of mu, and this precision parameter m. And as in the all previous cases, we have that the correlation will depend on m and the ni's. So this is what I meant when I said that we would focus on the quadratic variance functions, because in that case, we are able to prove this result explicitly, to find explicit form for the correlation functions. For other families, that might not be easy or even possible because we don't have yet expressions for the posterior variance of a conjugate family, for mu or u in this case. But in the quadratic variance case, we can do it, and this is what we did. Okay, that's the 6 cases. What I'm going to do now is discuss a simple illustration taking the inverse gamma model. We're going to model the monthly unemployment rates in Mexico from January 2006 to 2019. We're going to assume that the observations follow an inverse gamma distribution. And we already know the structure. We have u has an inverse gamma distribution. Conditional on u, the latent variables Si will have a gamma distribution, and conditionally on S, the observed process yi will have, again, an inverse gamma distribution. We're going to assume temporal dependence for the Q. So the set of neighbors will be this set. And we're going to consider Q on this set from 0 to 14. So here we have the data and a first fit for Q equal to 0. So as you can see, and this is just basically constant, and we have wide credible intervals. The fit is not very good. This is just for illustration. We can do the same for Q equal to 1. And the fit is a bit better, but still can be improved. We still have a lot of noise. So what we did was put this model through a model selection procedure, in this case, a simple DIC, deviance information criterion. And this shows that the best model seems to be the one with order Q equal to 11. So if we look at that fit, as you can see, we get a better fit. The credible band or credible region is much more concentrated around the fit, and it seems to be a good model compared with this one and this one. Okay, so for this case, we ended up with this fit, and it's a nice and simple model. So let me finish with a few concluding remarks. I already mentioned that we decided to work with quadratic variance functions because we have a more tractable situation. But even if we cannot find explicit expressions for the correlation in that case, we can expect similar behaviors, and they can always be computed numerically. But it's good to have, at least for these cases, closed form expressions. Also, it may seem too restrictive, but as I already said, these natural exponential families with quadratic variance functions contain very nice and important models, normal, binomial, and the corresponding conjugate distributions, as we saw, are also very well known, gammas, inverse gammas, and some others that probably are not very well known, but that might be useful, like the inverse beta or the scale student T distribution. Another feature of this model is because we are constructing these models based on exponential families and conjugate families. It's very easy to carry out inferences because of that conjugacy, particularly through Gibbs samplers or similar algorithms, because most of the full conditionals that are required are very simple, belong to the exponential family, and are very easy to simulate from. So we have specific algorithms to simulate from these distributions, or more general algorithms that rely, for example, on the convexity of these distributions. So there are efficient algorithms to simulate from that. For example, the illustration we showed was carried out using standard software. In this case, it was JAX, and it's very easy to implement. But even if we have to implement those ourselves, we have at our disposal several efficient algorithms. Another thing to note is that this general structure, or the procedure we described here, can also be applied beyond the exponential family. And in fact, Luis Enrique has worked with Gabriel Huerta on this kind of structures, where they go beyond the exponential family and work with a Pareto distribution, for example, which doesn't belong to the exponential family, but has a conjugate structure similar to the ones we studied here. So even in those cases, it's possible to construct this kind of models, which is very good. And finally, here we only dealt with a univariate case, but of course, we can also extend this to the multivariate case. The only thing is that in the multivariate case, the families are not that rich, in the sense that, for example, it's not easy to come up with a multivariate Poisson distribution. And the trivial one, which is just a collection of independent Poisson distributions, will have a quadratic variance function also in the multivariate case, but it's not very useful. Apart from the normal distribution, the multivariate normal, and the multinomial and negative multinomial distributions, the other families, analogous to the 6 we saw in the unified case are not very nice distributions. I mean, are a bit constrained. But anyway, we have this result, at least for the multivariate normal, we can do it for the multinomial, and we could even think about extending this to generalized linear models. So this is something that can also be done. So I think that's it. Thank you very much for annotations, and I will be happy to answer your questions or to listen to your comments.
Okay, gracias, Eduardo. Thanks. I have questions, but before I ask my questions, I will just check here in the chat if any student or anyone in the audience have any questions. Let me just invite them, though no questions yet. Let me just invite them to ask questions. I will do that in Português. Pessoal, se alguém tiver alguma pergunta, pode escrever aqui no chat, tá? Eu vou, pode ser em português mesmo, eu traduzo, mas não sintam-se à vontade para perguntar. Tem um delay de alguns segundos, mas pode perguntar aí enquanto eu e a Rosângela fazemos as nossas perguntas. Depois eu vou checar de novo aqui. So, before I ask my question, I will ask Rosângela first. Rosângela, do you have any questions?
Yes, very nice. I like the work, but I like to understand a little bit deep it. Now, because when conjugacy is like the key point here, né, to build the model.
That's right, yeah.
Yeah. Have you tried to extend the result for example, the skew normal family? Because there you don't have natural conjugacy, but you have a kind of conjugacy in certain way. And I don't know how difficult it would be if you don't have this natural conjugacy that's happened in the exponential family.
Yeah, that's a very good question, actually. We haven't thought much about that, but I mean, I think your question suggested the answer, because we can introduce another layer of latent variables in such a way that conditional those, you retain conjugacy, but marginally you obtain the distributions you want. Probably a skew normal. The obvious example perhaps would be to replace the normal with a t-distribution, where you know that you can write the t-distribution as a scale mixture of normals. So you can, as I said, introduce an additional layer of latent variables in such a way that marginally you obtain, in this case, the t-distribution, probably also skew distributions or some other types of distribution that in some way can be written as marginals of exponential and conjugate families. Does that make sense?
Perhaps, I don't know. I just like to study the paper and see what is going on, because could be some good thing to do.
Yeah.
I don't know.
I would be very happy to listen to your ideas. Yeah.
Yeah. Is it published, the paper?
Now it's submitted. It's in the archive. If you wanted, it's the last reference in this list, and it's submitted. We're still waiting for.
Very good.
Yeah.
Okay. And I had another question. Let me remember exactly what it was. Vinicius, I just forgot one thing that I need to ask to Eduardo. Then if you can continue before
Okay, so I'll ask my question. I was wondering, this question is kind of related to your future work. You have this, you have focused on this quadratic variance function. You talked about that on your slide 16. And you justify that by including the 6 families that are members that provide this property. So are you planning to study other formats, other formulations that may be interesting in this type of research?
Sorry, I'm not sure I got the question. You're saying studying other families apart from the quadratic variance function ones, or?
Or yes, apart from the quadratic variance functions, other types of variance functions, maybe including other families. So
Yeah.
Is that something that you plan for future work?
Well, we try to do it in a way, come up with closed form expressions for the correlation, which is probably the most important feature in these models. But we were not able to do that because we haven't been able to find expressions for the posterior variance of the mu, of the mean value parameter. So that's the point. From the applied point of view, that's not a problem because the model are well defined, and then we know we can simulate and do the Bayesian analysis. But we would like to have closed form expressions for this. We haven't been able to do so. That doesn't mean they don't exist, but we haven't been able to do it. But yeah, I mean, I think it's worth trying. No?
Okay.
It's interesting because the exponential family with quadratic variance function is really very special. It has very nice properties. And that's part of the work I did many years ago in that paper, the third reference there. If you move slightly beyond that, say, for example, if you consider the cubic variance function, then it's not that easy. For example, the typical member of that family is the inverse Gaussian distribution. And it's also a nice distribution, but it's more difficult to work with. It's one of those cases where, for example, the conjugate distribution might not exist. It might be empty if you are not careful. Yeah, that doesn't happen with the quadratic variance function, but it can happen even for a cubic quadratic variance function. So quadratic variance functions are very special. So I guess something can be done. I'm not sure analytically, but numerically, they are still well defined if you are careful.
Okay.
Yeah.
I remember my next question. Can you come back to the slide where you show the spatial correlation? I didn't understand what kind of correlation you are inducing by the model.
This one?
Because I cannot read it's like first, second order in neighborhood. Can you explain this for me?
Yeah, this is the page you want me to show? Yep.
What's the meaning of this graphic here? What?
Okay. Let me go back to this diagram. So we have 5 regions with this configuration, right? So we're interested in the correlation between region 1 and region 3, for example, region 1 and region 2, and so on, right?
Okay.
So
only regions that are connected in the space, for example, or
no.
You are investigating all kind of connections.
All kind of connections. For example, even Y1 and Y5 or 4. Yeah. In the marginal distribution, they will be connected. Okay. So this is just showing, for example, this is for region 1. Here at the top left panel. For region 1, the first line is just the correlation of region 1 with region 1 itself. So that's 1. The second line is a correlation between region 1 and region 2, which is slightly smaller. And so on. The last line is a correlation between region 1 and region 5.
Okay, that's good.
And the same for the other regions. So there's some redundancy here, but I think it's I think it's a good way to show the correlations. Yeah.
Well, my question is the following. You investigated separately for spatial correlation and time correlation. Yeah. But I am truly interested in how to connect things, correlate things that move in the space through time. Then I like to move. I like to correlate things in the space and also in time.
Yes, spatial temporal dependence. Yes.
Yeah. How is it possible to do it in this model in a simple way, or?
It is possible in a relatively simple way. Yeah, you have to be careful with the indices, but yes, this is what I meant when I mentioned this. For spatial temporal dependence, you can consider union and cross products of these sets. So you have to build the set of neighbors carefully, taking into account the temporal and the spatial dependence, but it can certainly be done. Yeah.
That's good. No, thank you so much.
No, but you're right. It will be nice to have, and we will work on that. At least a simple example showing this possibility, right?
Yeah, because
temporal, right? Yeah.
Yeah. I was thinking about, because I am applying I am looking for some spatial temporal relationship with data with the reporting, and you are using Poisson. Then I don't know what's going on at the end. Probably I can use your ideas to correlate space and time in my data. It will be so good.
Yeah, but you are using Poisson for the observations, for the observed.
Yes, for the observations.
Yeah, that doesn't quite fit in this framework, but it can probably be used. Yeah.
Yeah, I can think about. I can think about it because the idea is good.
Thank you.
Okay, so checking here the chat, no one have asked questions, so I guess I will thank Eduardo for accepting this invitation and to be here with us. Thank you for your time in presenting your work here. I will ask Eduardo and Rosângela to stay in the platform a little bit more while I finish here. And I will just say in Portuguese the final words to the audience. Pessoal, então vamos encerrar o seminário de hoje. Queria agradecer aqui ao Eduardo por pelo tempo dele apresentando o trabalho aqui. Queria agradecer também a participação da Rosângela e convidar vocês todos para o próximo seminário na semana que vem. Quem vai falar é o professor Wagner Barreto. Então, estão todos convidados, e aí até a próxima. Vou encerrar aqui a transmissão. Obrigado, pessoal.
Obrigado.